Okay,
Right, it
great.
seems working. Sure.
That's great. Okay, so the recording have just start, I guess. Is it everyone see the recording? Okay, recording start. Okay, very good. Recording start, so we can start this session. Well, let's start with the official things. Welcome everyone to this session of configurations and recommendations of our ICSE exit. And in this session, we have one journal paper, one journal first paper, one new idea and emergency results paper, one software engineering in practice paper, and two technical papers. And then we will go with the order list in the program, not going with the order listed in the mid place, like that is my instruction. So we will start with our first paper according to the program. The paper is a journal first paper, is predicting the objective and priority of issues reports in software repository. Okay. And the author, Abby, said that it is too early in his time, so he will not show up. And a couple of hours ago, he just dropped me a video and asked me to pay it. And the video is 6.5 minutes, so I will pay the first 5 minutes then. Well, okay.
Everybody, I'm Abbas Haidar Nouri from Sharif University of Technology. In this presentation, I'm going to present our empirical software engineering paper, which is titled Predicting the Objective and Priority of Issues in Software Repositories. This work was done by me, Ms. Maliha Izadi, and Ms. Kiana Akbar. For the motivation of the work, as we know, issue tracking systems are widely used nowadays by software development team because they provide very valuable information to the team. But in large scale projects, it's difficult to respond to all issues in a timely manner. So we need an approach to automatically predict the objective and priority of issue reports. This figure shows an issue report in a GitHub repository. As we see, an issue report contains very valuable information. For example, the author of the issue, the description of the issue, the labels of an issue, the participants to that issue, and many other information. And one of the most important information is the labels are the labels of an issue that somehow identify the objective of an issue. But in top 1000 GitHub repositories that we studied, we noticed that about 55% of issues had no labels. We also noticed that it's possible to divide the objective labels into three main categories, whether it's a bug report or an enhancement request or a documentation request. So our goal in this work was to propose a two-stage approach to automatically predict the objective of an issue and also its priority. Our proposed approach is the main steps of our approach is presented in this figure. I don't have time to go into the details, but our approach is based on artificial intelligence, machine learning, deep learning, NLP techniques to identify the objective and priority of an issue. So, uh, in a high level view, our approach is actually a two-step approach. In the first step, we identify the objective of an issue, and in the second step, we identify the priority of an issue. And as I mentioned earlier, we collected around 70 different information from an issue. And for the objective prediction part, we collected around 80,000 GitHub repositories, and from those repositories, we were able to collect more than 1 million issues. And we used the collected issues as the input data set, and we applied various deep learning techniques, and we noticed that the Roberta had the best results, and we were able to classify the issues into bug report, enhancement request, or a support request. For prioritizing issues, we again our data set For our dataset, we collected 83,000 issue reports from 70 GitHub repositories, and from those issue reports, around 45,000 of them were high priority issues, and 38,000 of them were low priority issues. And again, we applied various natural language processing techniques, machine learning techniques, deep learning techniques, and we noticed that the random forest had the best results, and we were able to classify the issues into high priority and low priority. For the evaluations of our approach, we try to answer 4 different research questions to see how our approach can predict the objective and priority of an issue. Also, in the third research question, we wanted to see whether our approach can predict the priority of an issue in a cross-project setting. And in the fourth research question, we tried to see whether our approach can perform well even on unlabeled data. These slides show the results of our empirical studies, and as we see, our approach had good precision, recall, F1 score, and accuracy. And also in our user study that we conducted to answer the fourth research question, we noticed that our approach can predict the priority of an issue even on unlabeled data with high accuracy. So as the concluding remarks, we noticed that our approach.
Okay, this is a journal first paper. So since the speaker is not with us today, so if you're interested in his research, feel free to go to contact him or study his paper. Okay, so we will be going to our second presentation by Martin, and his paper is a new ideas and emerging results. And the title of the paper is Better Modeling the Programming World with Code Concept, our graphic augmented multimodal learning. Okay, please go ahead.
Yeah, sorry about the title.
Sorry, yeah. Please go ahead
okay.
to share. Yeah.
So hi everyone, I'm Martin from University of Montreal, and I'm going to present this new track paper, which is about multimodal learning for code representation. So let me start right off with the context and motivation. So when it comes to code representation learning, the objective is to learn code vector representations, and the state-of-the-art learning paradigm is about what I'm going to present in these slides. It's composed of 2 phases. So the first phase is generally a multilingual pre-training phase, where we have a bunch of data set in multiple languages. We train a transformer-based model that learns the code vector representations. And the second phase is about fine-tuning this model for the task at hand. And so the fine-tuning is task-specific, so it's done on data-specific stuffs and on a specific learning objective function. So examples of tasks are left-to-right code generation. Examples of models for this task are CodeGPT and Codex. We also have code search that can be done with CodeBERT. We have code summarization that can be done with CodeT5, PLBART, and so on. So there are lots of tasks that can be done with this type of model. So they are very powerful, and they show great robustness, and they generalize pretty well on different data distribution and tasks. So that is, they learn from the syntax of the code because they take as input sequences of code tokens. They also learn from the global information of these sequences because of the architecture of the transformer that is based on self-attention layers. But what we can observe is that in programs, we also have a notion of concepts and compositionality. And the idea that we came up with in this paper is that we have high-level and low-level concepts that are manipulated in specific language constructs, such as identifiers and names. And so thus, this concept, from this concept, we can extract basically concept graphs. And so programs are highly multimodal. And so the question of this paper was, given all that, can we learn better representations of code to perform even better in the downstream tasks? And so we came up with a multimodal learning approach that is based on code concept graphs, where the idea is to joint learn a BERT-like language model and a graph neural network. So the graph neural network is based on the concept graphs, and the BERT-like language model is based on the code tokens. We show the applicability of this approach to code search, where the idea is to rank the best possible candidates given a natural language query. And we show that it works. It shows improvement over CodeBERT, which is quite a strong baseline, with a simple fusion technique that consists of a fusion of the graph embedding and the code embedding. So to conclude this presentation, I just want to mention some questions that can open the discussion. So a first question is, can we have large multimodal pre-trained models of code that are able to learn general purpose code representations? Should we fine-tune existing pre-trained models in a multimodal fashion, for instance, by defining task-specific modalities? And also, one very important thing is about the scaling law. So basically, the scaling law is that the more parameters we add in the network, the higher the accuracy on the task at hand will be. So we can derive several questions from that. The first one, can we observe the same trend with multimodal learning? How does multimodal learning compare to unimodal learning with respect to this law? Are the data processing and fusion worth the time and resources? So there's possibly a trade-off here. And that's it. So thank you. These are the author of the paper. So there's the Professor Huari Sarari from University of Montreal and Bang Liu.
Well, thank you. Thank you for the presentation. Yeah, so the flyby icon. Yep. And also in the meantime, when the presentation is going on, feel free to have questions in the chart. And yep, thank you for Livita. And then in your question, start with the presenter's name. So when we start the question session, then we know for whom the question is, to whom the question is for. So now we go for the third presentation. And then we welcome Eric for the third presentation in the area of software engineering in practice. And the title of the presentation is Dozer, Migrating Shell Command to Accessible and Synthesizable Modularly through Execution, Profiling, and our synthesis. Sorry, how come all the title is so hard?
And I also apologize for the name of the paper. So yeah, as said, my name's Eric. I'm presenting our paper on Dozer, which is about migrating shell commands to higher level configuration languages. And what I mean by that is if we take our tool, or a developer takes our tool, and they give it a command like echo some string into a configuration file, that is going to produce a change on the system, or that string is now on the file system in that file. And developers very often use the system shell because it's easy, it's familiar, but it doesn't give them the same benefits as something like Ansible or Puppet or Chef, which is this higher level language. And what we want to be able to do is have a tool where a developer can give us a shell command, and out the other end, we give them a correctly formatted, in this case, Ansible module that does the exact same thing to the system under configuration. And our insight for doing this is that if you're going to configure a system, every single program has to go through the system call interface. This is basically the API that the Linux kernel uses. And if they have a shared interface, you can observe that interface to infer the program behavior and make comparisons. So that's what we do, is we collect traces for a whole bunch of, in this case, Ansible modules as a target system. We store them in a knowledge base. And then when a developer comes to us and says, hey, I have the shell command, please tell me how to write it in Ansible, we will trace that shell command. We'll do a comparison between the traces that we have, and we take the most similar Ansible modules based on the trace comparison for our migration that we're going to produce. So here's what a system call trace looks like. This is for the rm command that removes a file from the file system. There's a whole bunch of stuff here related to just like standard loading of libraries. The important system call, at least as far as RM is concerned, is unlink at. And you can see that it takes a parameter, which is the same file path that is passed to the program. So that's important, right? That is information about what. When we do this comparison, again, we're doing it one-to-many, our source shell command to like all of the Ansible modules we know about. But when we compare just one trace to another trace, what we're really doing is taking all the system calls we know about on both sides, annotating where we see those parameters occur in system call arguments, and then we're finding pairs of equivalent system calls that occur in each trace, and we weight them based on how unique that pair is. So more unique pairs have a higher weight, they overall influence the score. And then we take an overall comparison score just based on the sum of all the individual pairs. Once we have a set of ones that are similar based on this comparison score, what we do is we take the input shell command, the similar Ansible module that we learned about, and this mapping of shell parameters to Ansible command parameters that we can infer. And we use it to generate a new Ansible module that is based on the definition of the one that is similar, but includes the parameters that the user passed using the shell command. And then we can compare the changes that they make to the system and see if they make the same changes that we are looking for. We pick the one that has the least differences, so they have the most similar changes. This actually ends up working really well. The echo command that I showed you before, using this technique, we can actually migrate it to the Ansible line and file module to add a line to a file. If you pass it something like apt-get install, we can pick the Ansible apt module with the state present and the correct package name, or RM for the Ansible file module with the state absent. So developers can use this to replicate the behaviors they do on the shell in a higher level configuration language. In cases where it went wrong, there are some interesting examples like make directory here. Make directory you think would be pretty straightforward because again, it's just a file path, but it turns out that the program for make directory splits the file path into its component parts and then uses them individually. And that makes it hard to do a comparison, which I think is very interesting. We did an evaluation on a number of common Linux shell commands. Overall, about 38 of them were successful. 7 of them, they failed in the migration for reasons like make directory. And then some of them either weren't supported by Ansible or weren't in the target data set that we had traced, and so we didn't know about them. Thank you.
Well, thank you for the presentation, and we will leave their question and discussion later. So now we go with our next paper, which is our technical paper, and we will welcome Wayne for doing their presentation. The title of the paper is Conflict-Aware Inference of Python-Compatible Runtime Environments with Domain Knowledge Graph. Okay, yeah, so this title is easier than last. Thank you.
Okay.
Welcome, Wayne.
Thank you for your introduction. Hello, everyone. My name is Chen Wei from Nanjing University. I'm going to present our work. In this task, given a single field Python code snippet, we need to infer a list of compatible Python packages with specific versions to generate a runtime environment. It can contribute to code sharing and the reuse of Python code and automated software configuration management. This is an overview of our approach PyCRE. The upper portion of the figure shows the construction of our Python package knowledge graph, which maintains a great deal of domain knowledge.
Sorry, wait.
The bottom portion shows.
I'm sorry, wait. It seems like your slide is not advancing. Are you still on the first slide?
No.
Yeah, I'm still seeing the cover preach. So
I will.
yeah, can you share one more time?
Okay. Okay. Can you see my screen?
Yep. Good. Thank you. Yep. Go ahead.
Is everything okay?
Yep.
Okay. The bottom portion shows the automatic inference of computable runtime environments. We design an ontology for Python third-party packages to represent the relationships between the entities in the real world. Neutral walk are submodel and attribute nodes and the requires age, which indicates the direct dependencies of the versions. To utilize the only input, we fully pass the target code into an abstract syntax tree and work for the imported models and the code attributes. The result of the code parsing can be used to infer Python versions. We define a matching degree based on the longest prefix match of the reference path. For each path tree, we calculate the matching degree for models and attributes in order to discover the candidate libraries. We propose a heuristic graph transfer algorithm for dependency solving. It has two heuristic strategies. One is priority. We perform the latest computable version. And the other is pruning. If one version of a package is incompatible, we skip the other versions with identical version specifications. And we use a set solver as the fallback for completeness. For the fairness of our experiment, all methods should acquire knowledge for the same Python packages. There are over 10 million entities and over 100 million relationships in our knowledge graph. As shown in the table, our PyCRE.
Yep. Also, wait. Seems like there's an advanced problem of your slide. Maybe you just like not put it into mode, just show it as a normal mode, because we are still at page 3 of your slide.
Sorry. I'm sorry.
Yeah. So maybe just keep it as the normal mode. It seems like it's not being shared.
Okay.
You can only click ask and go in the slide. Perfect.
Okay. Is everything okay now?
Yep. When it stay like that, then we can see the advancement. Yes, go ahead.
Sorry.
Yeah.
As shown in the table, our PyCRE is significantly better than the comparative methods in all different settings. Even with more complex process, the inference time of PyCRE is still short and comparable. In conclusion, we design an domain-specific ontology for Python third-party packages and an automatic approach to constructing the knowledge graph. We define a new metric of matching degree between Python libraries and third-party resources and propose an efficient heuristic algorithm for dependency solving. and other details are shown in our paper. Thanks for listening.
Candy, you are mute.
Sorry. Yeah. Thank you. Yep. Thank you for thank you. Wait for the presentation. Now we're going to our last presentation by Moshi, and then the title is Clear Constructive Learning for API Recommendation. Welcome. Go ahead.
Hi, everyone. Just let me share my screen. Can everyone see the slides?
Yep.
Is it full screen progressing?
Yep. It's full screen and progressing.
Okay. Okay, awesome. Okay, let's start. So, hello everyone. Welcome to the presentation. Today I'm presenting the paper Clear Contrastive Learning for API Recommendation. My name is Moshi. So API recommendation has been studied for years. It takes a programming question as input and return an API as answer. So currently there are 1.8 million Java questions on Stack Overflow and more than 4,500 APIs available in Java ecosystem. So there are more APIs adding to it every year. So finding the right API is more time consuming. So Biker is a leading tool for this task. It trains a word-to-vec embedding with Java posts. Then user provide a query to the model. Then it recommend APIs by comparing the similarity of the other posts and also API documents. But however, Biker is weak in modeling semantics. So in the example on the left, the answer from Biker missed the key API buffer reader. Biker thinks these two APIs are similar because they have same context. So this is because word-to-vec model gives static vector for token with same context. But that's not true, right? These two are essentially two APIs. So in the example on the right, Biker picked a post that has opposite meaning to the query. So this is because the bag of words representation is weak at capturing the sequential information. So we need better embedding to alleviate these problems. So now we propose contrastive learning for API recommendation. The advantage of contrastive learning is the model focuses on distinguishing whether the instance is similar at high level rather than learning the details of all the instances. So the learning goal is simpler and the generalizability is better. So this is an overview of Clear. First, we collect QA pairs and store them in a database. Then we construct post triplets for each post. Next, we train the model with contrastive training on a Roberta model. So the Roberta model generates 3 embeddings for 3 posts. Then the loss function updates the model towards the direction that minimizes the distance between the positive sample and the anchor, and also maximize the distance between the negative sample and the answer, the anchor, sorry. Next, the trained model is used for filtering similar posts from the QA database. So for each instance, top 50 similar posts are selected. The query and candidate are concatenated together as one input given to another Roberta model. Then we use cross-entropy loss for classification, so nothing fancy here. So in the search phase, a user provides a query, then the filtering model picks top 50 candidates again, then re-ranking model returns a least rank by relevance score. In the experiment, we use dataset provided by Biker for a fair comparison. We compare 3 tools as baseline. Also, we add pre-trained Roberta model without fine-tuning to better understand the effectiveness of our approach. We define the following questions. So first, how effective is Clear compared to other tools at method level? The result shows that we achieve an improvement of 21 to 104%, depends on the dataset. So second, how effective is CLEAR at class level? The improvement is about 7 to 62%. So we can see that the simple word-to-Mac model embedding has similar performance to the advanced model RoBERTa, while the RoBERTa model after contrastive training almost double the performance. So this shows that the major performance increasement comes from the contrastive training. So we also tested how random selection in the triplet construction affects the performance of CLEAR. We rerun the experiment 100 times with random subsample of the dataset. The average error is less than 1%, meaning that the random sampling effects is negligible. So these two diagrams representing the embedding space of the RoBERTa model before and after contrastive learning. So before contrastive training, the clusters are mixed and there are inputs in the gray dots that cannot be assigned to any cluster. So after contrastive training, the boundary of the clusters are much more clear. So in summary, we propose CLEAR, a contrastive learning approach to better capture the semantics of the API queries, regardless the lexical information. The result of our experiment confirms the effectiveness of CLEAR for both method level and class level. Thanks, everyone. That's my presentation.
Well, thank you, Moshe, for your presentation. So it is now question time. We have some question. So start with the first one. It is for Martin. How did you evaluate the applicability of the concept graphs? Maybe Martin, your mic is still mute.
I answer on the chat, but
Oh, okay.
I can answer already if needed. If
Yeah,
you need
sure.
more detail, basically.
Yeah.
Lavinia, maybe you can tell me if.
Sure, you can also explain for the recording to be
Okay,
available.
so okay. So for the evaluation, basically we focused on code search as the task. We took the code search net Java dataset, so we extracted from this dataset the concept graphs, and then the process is very basic. You have the graph neural network that learns the representations of the concept graphs, and you have the language model that learns the representations of the code tokens, and we do a simple fusion of the embeddings of the code tokens and the concept graphs to get the final representations, and we show improvement over CodeBERT. So that's it.
Well, thank you. The second question is for Eric. So I see you have answered there, but for our benefit, can you maybe share your answer again to clarify? So the question is, Eric, can you explain more about the scoring of the equivalence of our comments?
Of course. So when we're looking for two programs that do the same thing to the system by comparing their system call traces, like how they interact with the system kernel, it turns out that we don't really care about the order in which they do things. We only care about the fact that they do the same things once they are finished. So we treat all the system calls like a bag of words. It's a set, it's unordered. We don't care about tracing, you do this first, you do that second. As long as they do the same things at the end, it's good enough for us. So what we do is we take two system call traces and we just look for pairs of system calls in both traces that are the same. And we do some normalization to try and make sure that the representations match and equivalent system calls, because the Linux kernel has 3 or 4 different variants of system calls that you can make that'll do the same thing. We do some normalization, but we find pairs that are equivalent, more or less. And once we have those pairs that are equivalent, we count how many pairs there are, and the number of pairs tells us how similar those two programs are. The catch is, and there are 2 of them, I guess. The first is there's a lot of noise. So the RM example that I had in my slides, where you run RM and it removes a file from the file system, it was 20, 30 different system calls, and there was only one in there that actually exhibited the behavior of remove a file from the file system. Everything else was noise. We don't care about it. So we have to figure out how to pick out the things that matter and ignore all the ones that don't. And the way we do this is by weighting the system calls by their information content, which is influenced by how frequent they are in the data set of all system calls we have seen ever in all the tracing we've done. And more common ones have a lower weight because they give us less information, right? They're common, we see them all the time. More unique ones, we see them less often, so they give us more information. If it's unique, then it's probably important. So that's what we do. We weight everything, and then our overall score is just what is the total combined weight. And we normalize, but it's effectively just summing up all the different weights that we see.
Thank you. Okay, so there were two questions coming up. They are for Moshi, and then the first one is for Levator. This model could be used or extended for other languages that also have a great number of API. What will be the challenge for that? Like, what will be the challenge to extend that for other languages?
Thanks for the question. It's a very good question. So doing the work, I observed that Java is the somewhat most matured ecosystem for programming language. Like it has like so many questions on Stack Overflow, so it's a good source for machine learning related recommendations. But essentially, my model, like this model, is trained on the title of the question posed. So essentially, it's code, like it's code agnostic, right? It does not necessarily have to limit to any specific language. But considering that other language like Go or Scala or Python, they have less questions asked on Stack Overflow, so this certainly brings challenges on that. So I think the number of training instances is the limit. But essentially, the model is not limited to any specific language.
Yeah, thank you. And the second question for you is, yep. Seems like the network kept.
Yeah.
You want to continue? Go ahead.
I can hear everyone. Yeah.
Okay.
So the next question: how does your contrastive learning method compare to new contrastive and non-contrastive learning method like SimCM and VicReg? Could it be further improved? I haven't done any testing with these two new methods, so I couldn't really answer as of now, but I can certainly do more experiment on that to figure out whether it has better performance or not.
I see. Thank you. Yeah, and then so there is a follow-up question. So or Levator, can you can just speak it out? Just say your follow-up question.
No, I was just thinking that maybe Scala could work well because it's a Java machine based language. So the solution can use APIs from Java as well. I don't know how great it could work, but it could be a follow-up.
I see. Yeah. So
Yeah,
there
that's
other,
certainly a good direction to explore.
yeah. So any other question? Well, if not, actually, wait, while you're doing the presentation, it's kind of hard for us to follow up because the slide was not showing. Can you give us a quick overview, like just maybe a minute or two, saying that like, what is the suggestion? So basically, in your title, you mentioned about the domain knowledge graph that is going to be used to check for conflict in the runtime environment. So does it mean that there were some basic knowledge that were present in the graph, and then you can use that to do conflict verification? Is that their proposal?
Sorry, can you repeat your problem?
I see. No, can you give us like maybe a 30-second description about what is your paper suggesting? Mm-hmm. It is fine. Yeah, maybe I give you some time to think about it. Yeah, and actually I think we can have some discussion about the new ideas and emerging result, right? Because if it is a new idea, I think it is the idea have not existed yet. Okay. And maybe so Martin, can you further explain to us how is your new idea compare with other existing idea?
Yeah, that's a good question. And also it's a bit complicated because the field in deep learning for code is moving very fast. So we actually we submitted the paper in, I guess, October. And since then, there's been a lot of work in, especially in multimodal learning for code. But I would say that generally speaking, when it comes to code modeling, so this idea of learning code representations, usually the learning systems are based on, let's say, the code tokens, the abstract syntax tree, and they do not attempt to leverage other kind of abstraction that can be extracted from the code. And so also one important point of the paper was that we can abstract a higher level kind of data from a same source of information. So that is, we have the code, but the code we see the code as a sequence of tokens, right? But it can be further expanded to lots of data modalities. And this is what we've shown by extracting concept graphs of identifiers. And we've shown that it can improve a learning system using a simple fusion. So essentially, it prompts us to investigate further this idea of multimodal learning, and especially with large language models, because these large language models, they are based only on sequences of code, and perhaps they could be further improved with this idea of multimodal learning.
Mm-hmm. Thank you. Yeah. I honestly admit that this is not my specialty area. So because they run out of volunteer, they just want me to chair it. So I just want to understand it so that the graph that you generate will actually help human being to understand the system, right? Is it the what
No,
it is?
No, it's not about interpretability of the system. It's about making the system more efficient, more effective on the task. And so the idea is that when you have a transformer-based language model, it learns from sequences of tokens. And on the other hand, we could have graph neural network that learn structural information. And so the idea was to combine both kind of information that can be abstracted. And this is interesting because the graph neural network with the message passing function inside it can allows us to learn local information. It's difficult to explain without all the background, but basically the message passing is the idea that the representation of one node will depend on its neighborhood. And so there is a locality in the graph that can be abstracted in the representations. And on the other hand, with the transformer, we have kind of a more global information that is abstracted because of the self-attention in the transformer. And so the whole point is about combining both kind of global and local information. And so I think that for the future, having that kind of multimodal paradigm is very important. Yeah.
I see. So the benefit or the future goal is that through this model, you can identify how to make the program better, like or identify area where the program can be improved. Is this the ultimate goal? Like, so analyze the program, get the graph, and then see like this maybe there might be an improvement area that you can work on. Is this like the benefit that's like
yeah, that can be the benefit, especially as we can think about lots of data modalities that can be extracted from software artifacts. And so if we manage to find, let's say, if we want to build a recommender system that is based on a deep learning systems, then perhaps it could be useful to have specific data modalities for the task that we want to target, so that we will improve the system, the recommender system, and then we will improve essentially the recommendations for the developer and the system at the end.
I see. Well, thank you. And there's a question from Eric for Wade. When you generate Python environment, did you generate only a single environment, or did you test multiple environments? If the first doesn't work, if the first environment doesn't work? Yep. Yep. Wait, this is a question for you. Well, yeah, maybe there like some narration. So I have a question for Moshi, and I like let's just clarify my understanding. So for your research, basically you like get all the search criteria for Stack Overflow, and then you get the correct answer, like the correct API from one of the answer. Do you just get the one that marked that as correct, or do you personally check the criteria and then personally find the right API?
Yeah, thanks for the question. It's a good question. So when we do data collection, we select only the accepted answer.
Mm-hmm.
So essentially, this data set is built by Biker, right? So they take only the accepted answer as training data, and they extract the APIs from the answer from the code snippet as the label, essentially. Yeah.
I see. So in that case, like because that one answer might be correct for, let's say, for Java 8, it might not be the right answer for Java 11 and now 17. So have that different version of the API be considered?
The training data is collected on Java JDK version 8. So it's quite old. So I agree that there are some obsolete APIs, of course. Yeah. So yeah, if we were gonna use it in the industrial, we have to redo the section for sure. But there are Stack Overflow data dumps, and there are Stack Overflow Explorer, so the data collection is not that hard. It's available. Yeah.
I see. Yeah. So just wonder, Wade, do you see the question in the chat? Did you want to try to answer that? Yep. So Wade, there's a question for you in the chat. Yeah, if you take a look, would you like to answer that?
I'm sorry, I can't see the problem in the chat.
Oh, I see. The question is, when you generate Python environments, do you generate only one single environment, or do you test multiple environments? And if the first one does not work, then you keep generating for a different environment.
No. We only generate one runtime environment. and we do not check it.
I see.
Uh,
Yeah. Okay. Yeah. And so anyone have other questions for our speaker? Well, if not, I want to thank you everyone for your presentation, and then well, all the best for the rest of the conference. Enjoy yourself and make connection, have fun. Okay.
Thank you.
So thank you. Take
Thank you.
care.
Thank you.
Thank you.
Thanks.